Okay, now it looks better. Okay. Guess we'll start in a minute as people get her up. Okay, looks like we have quorum. Okay, thanks all for coming in the morning. We're nearly there, a few more lectures. But today we're going to talk about clock generation. So we're building big digital chips, but there has to be a source of clock on that chip somewhere. And especially as the ASICs and the big SoCs are working in multi-gigahertz frequencies, you need kind of to bring in a lower frequency reference clock that usually comes from, let's say, a crystal on the board. And then you want to be able to manage the clock frequency multiplied up on the chip. And also, as we've seen in the, for example, DVFS lecture, we want to be able to actually scale that frequency to arbitrary continuous range of frequencies, right? And figure out how to do that in orchestration with the whole clock distribution network and the rest of the compute units in the system. So we're going to take a look today at how do we generate that clock that's arbitrarily or as desired multiplied up and then controlled, and what are all the noise sources that participate in this, and why is that important? Well, when you're doing PNR, you have to set your clock properties, right? So you have to say what jitter, what uncertainty are you expecting. Yeah, then the tool goes and budgets the rest in terms of kind of inserting the clock buffers, etc. But you have to kind of anticipate based on the properties of your system, your clock generator, what are those uncertainties that are coming into the system, and kind of annotate them in the tool so you can take appropriate actions to size up the pots and all the clock distribution in such a way that in the end your yield is high, right? So there's a little bit of a predictive process going on here, and you need to kind of understand what type of PLL do you need. For example, PLL standing for a clock generator, what noise properties it has, what supplies should it have, right? And have just a normal regular digital supply or some other kind of supply, how sensitive it is to all those types of noise sources, and how should you protect it in your floor plan, in your circuit. Modern systems can have many PLLs in the system and have them kind of, let's say, on a per core basis. And then how do you synchronize that up? Okay, before we kind of go through into all that, some announcements. So next Thursday, so not this one, next one, in class, actually, is it? Yeah, it's, so it's gonna be in class final. So 80 minutes, so we start at 9:40, finish at 11. we'll try to design a final so it fits within this time, so you're not under time pressure to do it. And then we have in the RR week, we have project presentations, because there's quite a few projects. We're gonna have a chunk of time dedicated from 9 to noon 30 in Berkeley Wireless Center. Hopefully everyone knows where BWRC is. If not, ask your friends. We'll kind of let you in at a bit before 9. There will be people there. And each presentation is going to be 12 minutes plus 3 minutes Q&A. So we can kind of pack everything in 3 hours. Yes? Is our final on Gradescope or is it? Excuse me? Is our final going to be on Gradescope, like the quizzes, or is it going to be a written exam? No, it's going to be a written exam. Yeah. It's going to have some things to write and things like that. So please aim for this time, 12 minutes plus 3 minutes Q&A. And I think Bora promised lunch after this. I don't know, he can chime in next lecture, but I think that was the plan. So at 12:30,
we'll give it a try.
Yeah, we're all gonna, and that's partly the reason we're doing it at BWRC. There's nice space outside, and so we can all get some food. Okay, so those are the announcements. So today we're gonna look at the clock generators. Phase lock loop is basically a way to generate the clock in the most flexible way, in a sense of being able to multiply it up from a reference and things like that, as we'll see. And then we're gonna also talk first about the basics. How does the loop work? What are noise transfer functions? How does the noise propagate? And then we're gonna look at some relatively recent trends as of last 10, 15 years of people trying to digitize these systems, which were inherently analog, in being able to proliferate them more freely throughout the big SoC and being able to integrate them, even design them mostly with digital tools. That adds additional level of complexity. So we're gonna first go through the basics and then give you a little taste of what it takes to understand digital PLS. Of course, there's a lot more to be dug into that, but we don't have necessarily the time to go into all the details. So first, looking at the phase lock loop basics, what does the loop look like? Essentially, phase lock loop, as the name says, it tries to produce a clock at the output that is phase locked with, or phase and frequency locked with the incoming input reference clock. Now, a very high level, systems block diagram is essentially something like this, right? Where in the phase domain of the clock, we're producing the phase of the output clock has to basically subtract from the input reference, and there's a low pass filter and something that generates the internal clock, which is a voltage controlled oscillator internally, but essentially there's some transfer function, right, in the loop. So it's basically a closed loop negative feedback system that tries to enforce that phi out tracks phi in. Now, there may be differences in the frequency of phi in and phi out, right? And so this kind of more detailed implementation diagram kind of shows it. The PFD is kind of the analog of trying to figure out the phase difference between the input reference and the output clock. And then the charge pump and the filter essentially work as jointly as a loop filter that tries to filter that error information from here to steer the local oscillator into a proper phase and frequency position. And that local oscillator is the voltage controlled oscillator. Now, if you add a divide by n here in the feedback loop, if you just look at kind of the control theory analysis of the loop, it essentially ends up having the effect that it multiplies this frequency up by n times the Fin. Now, alternatively, you can put a divider in front of f in. Let's say a divide by m, right? That way your f out is actually n over m times f in, right? Because now your reference is f in over m. So you can, by tuning m and n, you can essentially get any rational number ratio between the output clock frequency and the input, right? Now, depending how we design this loop filter, it will have different properties in accumulating this phase error, right? And how the VCO reacts to that phase error. And that will set the loop dynamics and give us some ability to essentially both compensate for the phase error, having kind of a static phase error go to 0, but also be able to track the frequency errors. Now, loops typically don't have infinite frequency tuning range, so you have to kind of bring these two frequencies in reasonable proximity so that the loop can actually do its thing. And there may be additional circuitry needed around this basic structure I'm showing you to kind of do first the coarse frequency lock, and then after that, this loop takes over and makes sure it tracks the frequency and phase. But those are kind of some additional things to consider. Okay, so to better understand the loops, we're gonna do like a part-by-part examination of what is actually the transfer function of each one of these pieces and how do we then put it all together. So the heart of the clock generator, or the phase lock loop, is essentially the voltage controlled oscillator. Right. So what it does is it has some free running frequency and then proportionally reacts to some control signal to change the output frequency, right? And so your output is really some amplitude cosine, or it could be a collection of cosines, like in a ring oscillator we're going to see later. You don't quite get the cosine, you get like a pulse train. But the base fundamental frequency of that is going to be essentially what we're tuning. From this kind of view, we can extract the relationship. It's basically a linear relationship from this function of the output frequency versus the control, right? Which means that the phase is actually an integral of this, let's call it delta omega, right? That you're creating. Because you have the base plus some delta omega you're introducing the control. So the phase is delta omega times t, right? Or integral. And so because of this integral function, the transfer function of our VCO is in the S domain, or in the, if you will, in the frequency domain, or is KVCO over S. So if we look at the possible implementations of this ring oscillator, or VCO, it's one example is ring oscillators. And it's basically, as we know, a string of inverters, but you have to have a way of controlling their strength. Controlling their strength controls the delay, and therefore will allow us to change the oscillation frequency of the ring oscillator according to some control signal. So, for example, this one has essentially a V control that kind of adds additional capacitance to each stage, allowing you to kind of slow down all the stages in the ring oscillator and establish some sort of voltage frequency curve. The other one is the control actually affects the current or ion of each of the stages, and therefore, again, affects the delay, right? Because our delay is going to be like I over C, some proportional, right? or inversely proportional. And so there are other ways to build a ring oscillator. For example, I could build an RLC circuit or LC, right, and active. Those are typically rarer in big digital designs, simply because you need area for an inductor, you need to block everything out. And the high frequency, the jitter is much smaller in those types of LC oscillators than in these ones, as we'll see. But you're not running AC clock frequencies so high that you really need that type of oscillator. This is typically used in, let's say, high-speed I/O, where your bit time is nowadays like 10 picoseconds or 20 picoseconds, and therefore you cannot afford a lot of timing error on that. You typically want, like 0.1 picosecond type root mean square errors on that clock. Here, if you have a few gigahertz clock, you can afford to have a few picoseconds of jitter and total at the output of your, let's say, clock generator. So these types of ring oscillators are reasonably good. If you want to improve on that noise, and we'll see kind of where all the noise sources come from, but in this, for example, oscillator, you have the thermal noise of each stage, right? Plus you have the supply noise on each stage. And we know that the inverter delay is directly proportional pretty much to the level of the supply, right? So imagine perturbing the supply by 1%, you're going to get a proportional response in the time delay, right, at the output, which means that you would be highly susceptible to supply noise in this type of voltage controlled oscillator, right? So if it's a harsh digital environment, you may decide to actually, instead of like doing, current start, additional capacitance or current starting, both of which degrade the edge. And because they degrade the edge, they actually increase the impact of voltage change on timing, right? Because the slower your edge is, the more timing error. I don't know if I have this is a disaster. Okay, well, anyway, you see this line roughly. So if I have, oh man, this one is probably not useful. Anyway, if you have a very sharp edge, right, then small voltage change. Oh, thank you. Yes, scarcity. Yeah. Okay. So let's see. Okay, that's a little bit better. But you have these two cases, right? So here in the very slow edge, small voltage change results in big timing error. Here, a small voltage change results in small timing error. So if you have a well-running ring oscillator, right, with very small delays, so sharp rise times, that one is less susceptible to supply noise, right? Because you're going to, or even its own thermal noise. The transfer function is smaller because it will actually change the voltage, but that doesn't affect the timing that much. However, once you start messing with adding additional clock loading or starving the current, the slope is going to become less. And now thermal noise or supply noise transferring to the output will become larger. You can actually characterize that response on a per stage, and it's called impulse sensitivity function. So you can apply a small current spike, like a thermal source, noise source within the inverter or on the supply, and measure the output around the edge. So if I apply a little spike or I can do a little step response and then figure out the impulse from that. But I can do a little step on the supply or on the control or on the basically kind of the current of the inverter stage as well, and sweep that across the edge, the timing edge. If I apply a small noise here, it's actually not going to affect my timing at all, right? Only it is around the edge that any noise is going to add to timing. And so if you sweep this across, you're going to get some response. You do a derivative of that, that will be kind of, for this timing point, your response, your impulse response. And then as you sweep this across, you're going to get the overall impulse response of the noise impacting the system. That's called impulse sensitivity function. So you can characterize every oscillator type or every delay stage type. It's not only just oscillators. We'll talk about the clock buffers later, right? And you can characterize their impact in transferring any kind of noise source into the timing noise. But so one way to avoid, for example, this type of sensitivity is to use a voltage regulator as something that regulates the VCO, right? Now, reducing the voltage, the supply voltage of the VCO of the ring oscillator, of course, will also lower the edges, right? Because we are scaling down the current, the drive current, right? However, the regulator will do some supply noise rejection, right? Because up to regulator bandwidth, it will try to essentially track whatever is the reference here. Right? So it's not gonna, it's basically gonna reject whatever comes from the supply. Of course, after past the bandwidth, it's gonna give up. So any higher frequency noise will enter. The nice thing about that is that the VCO itself, as we've seen, and we'll look at some actual noise transfer functions. Remember, it's kind of like integrated, right? So any noise that comes in, it will basically get integrated. So if it's high frequency noise, it will be rejected a little bit more than the lower frequency noise, right? So this is kind of one popular way of essentially building something that is a bit more robust to supply noise in these digital systems and potentially not having to have a very, very clean supply here on the VCO. Alternatives are that you have to bring in very clean supplies, so-called analog supplies, route them on the chip where you're installing the PLL, make sure they're properly coupled up, or even actually analog VSS. So there are different theories about that, but that's extra floor planning stuff you have to do to be able to protect the PLL supplies. But if you add the regulator, you have a little bit more relaxed kind of environment. Okay, so as we mentioned, the VCO integrates, right? The phase, the control voltage error, because the control voltage error affects the frequency, and then the phase is an integral of frequency. Right? Now, there are other types of control things, like for example, where I don't need to multiply the clock. I'm going to use the same frequency and just want to basically adjust the delay in a controllable manner. Then I can turn my ring oscillator into just a delay line, right? And then compare the output to the delay line to the input of the delay line and lock that, right? That's called a DLL, or delay locked loop. Similarly, if I have a clock buffer chain, as we've shown here, on every inverter, you're going to get a little noise add, right? So in the VCO, as you're going around the loop, on every inverter, you do a little bit of noise, but you feed back and then you add a little bit more noise and feedback, and so the noise accumulates across the ring oscillator, right? In a clock buffer chain, the noise is just the sum of however many buffers you have, right? So it's not going to be an integrator in a longer clock buffer chain, but it's going to be some sort of a low pass filter, right? Because it takes some number of these noise sources and adds them up together, right? So it will accumulate, but limited. It's not going to be basically 1/s, right? And then you're going to see that kind of as we look at the transfer functions. But it's important to keep in mind, because post PLL, you will have some clock buffer tree, right? And you may decide in your design, depending on what you're doing, to even regulate part of that tree before it starts being too unwieldy, at least down to kind of a local clock domain, or provide a separate clock buffer supply that will kind of minimize the supply noise on that clock buffer chain. Because if you're not careful, you can completely kill all your good efforts on the PLL. You can have a super clean PLL, very crappy clock distribution. In the end, you still have noise because you had many buffer stages, let's say 10, 20 clock buffer stages before you reach your source or destination flip-flop. Okay. Another element to understand is how do we extract the phase error, right? We had this phase frequency detector at the beginning. In the loop block diagram is just a fancy summer, compares the two phases. How does it do that, right? And there are many circuits how people do that. We're going to talk about two today. One is kind of in the context of analog PLLs, and one will be for the digital. The kind of a staple phase frequency detector is this 2 flip-flop with a reset block. And what that allows you to do, so both flip-flops are tied to a 1 or VDD. And then you have inputs A and B. These are your like reference clock and feedback, for example, right? And so you see what happens here is that you're essentially providing once each of these triggers, because the 1 is coming in, right? If you're, let's say, initially reset, then as these two trigger, they basically sample this 1 whenever they are arriving, right? And then you're ending that to reset back again. So what you're creating are these pulses that show you, where the width of the pulse show how much non-overlap between the two blocks you have, or how much phase error. So in this case, what you see is that let's say in here we're having kind of a not only a phase error, but we have a frequency error between the two signals. So you see that as this period is larger than this period of A. Right? So you see that as you move on from clock cycle to clock cycle, this difference between the two pulses basically becomes wider and wider. And so your signal, your phase error signal accumulates. So QA is like your phase error signal, right? It'll give you the width. Its width is basically proportional, or if you average that signal, another view is you're getting a proportional measure of the phase error, right? In this case, it accumulates, right? As we go in time, basically the average will grow, right? In this case, it's the pulse width is constant because the two waveforms are the same period. They just have a phase error, right? So this type of detector is basically called a linear phase frequency detector, because in its detection range, which is plus minus 2 pi difference between the two inputs, it gives you kind of a linear response in the average signal at the output. Now, the tricky thing of course, is that information is hidden in the width of these pulses coming up, right? It's not immediately some control voltage I can use to drive the, let's say, my VCO, right, that we discussed previously. So I need some way to convert these little pulse blips into an actionable V control that can influence the voltage controlled oscillator. Right? So how I do that? Well, that little analog block or switched mixed signal block is called a charge pump. So what you do is you have two current sources. Ideally, they're matched, so they're both the same current I. And based on these signals, right, one signal will essentially say, okay, increase the phase or frequency in one direction. The other signal will say decrease, right? And so based on these, you will integrate or discharge the capacitor from these two current sources. And that way you're kind of turning the pulse width of the phase detector into an average voltage. You're basically collecting the charge under the pulses as they're going through. So this is a little diagram that shows that. So for every pulse, right, we do a little integration, and then there's nothing, and then there's a little bit of integration, etc. So the overall, there's still a little ripple, right? There's a little staircase, because after all, this is a sampled system in a sense that every ref clock, something happens on the input, right? And so you get these little updates. So if I apply this directly to the VCO, VCO has to kind of integrate a little bit now this as well, right? But this slope is proportional to the current that I have in the charge pump. 2 pi comes from the phase detector, and then you have a CP, right? Okay, so I can try to immediately tie this, because now I have some control voltage that comes out of the charge pump, where like at this point here, I can add it to the VCO and see what happens, right? The first thing to do is to kind of see what are the transfer functions of all of these blocks, right? So for the phase frequency detector, as we've seen kind of previously, it effectively has a linear relationship between the phase error and kind of the, let's say, the notion of average voltage, right? So we have the phase detector, and then because of this integration, we have to add S, right? So that's our first integration part. The VCO, we already said, was KVCO over S, right? And now that's our low pass filter. You can call that this first low pass filter, and HVCO is this term here, right? And then just normal feedback loop, I get essentially H over 1 plus H, right? Where H is this total transfer function. And you see immediately we get like a second order thing. Okay. Now, this has a bit of a stability problem, right? And so the way we can compensate that is by changing this integration capacitor to add a 0. So we have now an RC. And we can tune the size of the CP and R to try to kind of minimize the ripple in the control voltage and kind of provide, just like a normal second order linear system, I can essentially get the damping factor and the natural frequency adjusted based on these parameters, essentially the charge pump current, the charge pump capacitor, as well as tune kind of where my 0 needs to sit with the RCP, right? So I have some degrees of freedom in which I can adjust this control loop to do what I want. Now, fortunately, there's some natural capacitance forming here that we're not taking into account, right? I did just design this loop filter. But there's some wire, there's some input referred capacitance of the VCO itself, right? Or that control input that I still need to take into account, right? So, so there's like another natural pole that exists through this Sp22, right? And so that's, yes, it gives you additional filtering of the controlled noise voltage, but it lowers the phase margin. So you kind of need to go and take it into account when you're doing your loop dynamics to be able to properly position how you want the loop to respond to this. Yeah.
What do you mean with a zero in the previous?
So this is a transfer function, right? It has two poles here because it's second order, and it has a zero here. Right. So you can essentially tweak where the zero is to lift the phase margin and basically improve the stability. Okay. So one thing that we want is to adjust the loop dynamics so that it basically does the job of tracking both phase and frequency errors, right? And producing the right multiple of the clock that we want at the output. Now, another very important thing is we want to understand the loop dynamics so we can understand how the noise propagates through the loop, right? And so if you look at the input to the output relationship, right? And let's say, look at kind of this is the overall transfer function, right? It's regardless, even if we have a zero here or a second pole, it's going to be a low pass filtering type transfer function. How underdamped or critically damped or overdamped that's a choice for you based on these parameters here. So that may end up with a little bit of peaking here or not. That's your design choice, depending how fast the response you want in the system. But inevitably, it's going to be a low pass from the input to the output. Right? So that's the first thing to keep in mind. Whatever input noise you have, right, the low frequencies are going to just sail right through the PLL. It's not going to do anything to them. But any higher frequency noise at the reference will get low pass filter. Now, another thing that we talked about already was the VCO and its own noise, right? We talked about its own thermal noise, the supply noise impact on the VCO, etc. And so it's useful to think about, okay, well, how does the loop react to some phase noise of the VCO, right? That the VCO injects into the whole loop. In that case, it's injecting it, I'm showing here at the output. I can always, if I have supply noise, and I'll show you a few slides later, if I have supply noise will transfer to VCO output through this mechanism over here, right? And of course, accumulation. And so there will be a transfer function from supply, let's say from the supply of the VCO to the output of the VCO. And then I'll be able to establish what is the output referred phase noise of the VCO. That's this phi VCO. Now I'm interested in how this phase noise of the VCO affect the output phase noise, right? And of course, you can just do a simple derivation, right? Just set this to zero, follow this throughout around the loop where this is some global H, right? And what you're gonna see is that, of course, if you think about it, it should be like something of like 1/1 plus H or something like that, right? So it's gonna create effectively a high pass response, right? What that means, in other words, is that if this was a disturbance with very low frequency, right? Then the loop, because it's within the loop bandwidth, should be able to track it and reject it, because it really wants to match this to the clean reference, whatever it is, right? So that's exactly what's happening over here. effectively any disturbance that you have in the output, the loop figures it out and rejects it, right? You dink the phase a little bit here, it goes through the loop, creates the error, goes through the filter, and creates the opposite phase here that cancels. And as long as the loop can track that, which is these lower frequencies, the loop rejects it. But it doesn't reject the higher frequencies, right? So now the key is to set the dynamics of the loop. So to increase the, from this standpoint, I would want to increase the bandwidth here as much as possible, right? To be able to suppress as much of noise as possible in the system, right? But I can't necessarily increase the bandwidth of the loop indefinitely because of stability, right? It has to be, the loop bandwidth has to be some fraction of the reference input frequency for me to be able to design a stable system. So there is like a trade-off there. How high of a loop bandwidth can I achieve to essentially, if we go back here, if I'm increasing the bandwidth, I'm going to become a bit less stable. So I'm going to have some peaking here. That peaking is going to amplify the input noise, right? So there's going to be a trade-off between how much of the input noise you amplify versus how much of the generated noise in the VCO you suppress. And there's like a little sweet spot there, which usually people use, knowing what their input clock is, knowing what their supply noise situation is, what type of regulation of the VCO they have. You can kind of figure out in models where the sweet spot is in the PLL band, right, and set it there. I'm mentioning the input clock because you feed the input clock from the crystal outside. It has certain properties, but you also need to buffer it on chip. That there you also add noise, right? And so if you're not careful, you create too wide a bandwidth of PLL to suppress the VCO noise. You're now admitting all that reference clock noise into the system. So you gotta be careful. Because remember, clock buffers at higher frequency noise, right? And it's going to be right about where you're peaking in your loop bandwidth, so it could be pretty nasty. Okay. So how do we take kind of like a pictorial look at what are all the things that we just talked about, right? So we talked about the input, the noise transfer. By the way, these are called noise transfer functions, right? If I'm looking how something propagates through a control system, like a PLL, it's going to be a transfer function. If I'm looking at how noise propagates, that's a noise transfer function, right? So if I'm looking at the phase noise of the reference clock, going through the whole PLL, right, that's, as we said, going to be a low pass. And depending on the loop dynamics, there may be a little bit of this peaking, right, in the system, as I'm trying to kind of boost the bandwidth in the response to the PLL. Now, if I look at the VCO here, right, now in this case, so in the previous case, we were looking at the phase noise at the output of the VCO, right? How does it propagate to the output of the system, right? And that was a high pass. It was a high pass simply because the loop was rejecting the low frequencies here. Now, what I'm actually interested is in the noise transfer function from the supply to the output, right? So there's additional little transfer function. How does the supply voltage transfer into the timing error of the VCO element? Then how does that timing error of the VCO element affect the overall VCO phase noise, right? So remember that VCO has this integration thing, right? So whatever supply error I introduce here, that proportionally causes the time error, the phase shift, that gets integrated across the whole VCO, right? So that's this integration slope over here. Right? So you normally have, from the VCO output to the PLL output, you have this transfer function. you need to multiply it. If you're now projecting what happens from the supply input to the VCO to the output, there's additional 1 over S, if you will, or KVCO over S transfer function, or it's not going to be exactly KVCO because it's going to be some K supply VCO over S, right? But it's still going to be some impact of the supply on the VCO phase. And that's going to have an integral, 1 over S curve. So you multiply these two, right? You will get a shape that looks like this, right? Which tells you that, okay, in the low frequencies of supply noise over here, the loop rejects that phase noise. In the high frequencies of the supply noise, the VCO will integrate out or average out that high frequency supply noise, right? So you have these two mechanisms, and it ends up being kind of like a bandpass. And then we have the clock buffer, right? It depends where you take the feedback. So some clock generator designs include a little bit of a clock buffer to be able to kind of get some additional understanding of where the phase noise comes from in the buffer chain and try to have the loop compensate for that. Clock buffer is though not a VCO, right? As we said, clock buffer has some limited number of stages, so it doesn't accumulate indefinitely. It only accumulates, let's say, n error or noise events, right? So its transfer function is going to be sort of a low pass, if you see the roll off here. And of course, the lower frequencies of noise, just like in the output of the VCO case, are going to be tracked by the phase lock loop. So these lower frequencies of basically this green function are tracked out by the PLL. And it naturally slopes down after some frequency. So this window basically gives you kind of what's the duration of your, let's say in this case, the total clock buffer delay was roughly a nanosecond, right? So 1 over that gives you kind of like a gigahertz-ish bandwidth on that low pass filter, right? It's much wider than the PLL itself, right? So the noise can get in all of this regime, right? High frequency noise can get in and mess you up. And the loop cannot do anything about it because beyond loop bandwidth, right? So that tells you that you really need to be careful about this clock buffer, right? Now, these are just noise transfer functions. In order to calculate the end noise, you actually need to know what's the spectra of the noise coming into the system, right? So in this case, I'm drawing these kinds of things. So for the phase noise of the ref clock, it's an oscillator, right? So its own phase noise is going to look like basically 1 over S squared, 1 over S cubed, depending on kind of the flicker or thermal noise of that oscillator, right? So its power spectral density is going to look like that. And that's what we're plotting here, right? So you're going to take that power spectral density, multiply it by the square of this noise transfer function, and essentially get the output power spectral density, right? The supply noise, I mean, you can kind of think it's high pass, it's a low pass. I mean, it has to end at some frequency, but you will have, depending on the digital system, you'll have highly non-white kind of spectrum, right? You will have, first of all, a lot of spurs at clock and clock multiplies of the clock, because a lot of registers are transitioning at the same time. So your supply noise signature looks like very bursty. And then there's a little white noise depending on your logic depth of each stage as the logic is transitioning. And as we know, logic transitions at some random activities, right? So you're gonna get something like, okay, this I can't draw, but you know, you're gonna get some burst and then some burst, right? So you could do a Fourier transform with that and see kind of what spectra that gives you. It's gonna be pretty broadband, but eventually will roll off, right? And so that you can apply that type of, and of course you have decoupling cap and all that, but definitely you have something like this happening. And similarly on the clock buffer. So you can use these kinds of estimates and essentially figure out what is your overall noise transfer function. And this is an example of doing exactly that. So when we multiply effectively these noise sources, then you're getting really now phase noise here plotted. And you see that within the loop bandwidth, okay, we basically are tracking all the noise that's coming from the ref clock. And then the loop suppresses that. Or basically the loop cannot track it beyond its own bandwidth. So it naturally gets suppressed. And then you have the VCO noise. Again, you have kind of, this is your normal 1 over S, but then let's say the limited roll off of the input kind of supply noise kicks in, and similarly for the clock buffer, right? So in the end, you get some phase noise that looks like this. Okay. The key takeaways here is that if you look at basically this, what is the overall phase noise for anything that's below the loop bandwidth, right? Reference clock really dominates. Right? And anything that's above the loop bandwidth, really the supply noise or the VCO noise and clock buffer noise is going to dominate. And in that, the supply noise is much more dominant, at least in these types of digital systems that we're talking about, than the actual thermal noise of the VCO itself, right? So those are kind of the rules of thumb in designing the system. Okay. This gives you hopefully some understanding of how the PLL works as a control system. And so far we've looked at kind of, let's call it the analog / mixed signal version of a PLL, where we're detecting the phase signal, turning phase error into pulses. We're then integrating these pulses to get the voltage control, and then we're controlling through that voltage an oscillator. It's kind of like a lot of tricky analog components to do there, especially the charge pump, the filter, how do you regulate the VCO, etc. So people are trying to gradually go and replace all these things with something that's digital, that can be much more easily reproduced on a big digital chip and in kind of more digital friendly processes, right? The trick is that now we need some way of turning that phase error into something digital, right? So what would you use? What do we use to turn some analog signal into a digital signal? One example. What? ADC, right? It's just the fact here is we don't really have an ADC turning voltage, analog voltage to digital representation. We need to turn time or phase into digital representation, right? So typically people call these like TDCs, time to digital converters, right? So what's the simplest time to digital converter or analog to digital converter? Yeah. That is possible, and something like that people do to create a more precise TDC, but like I'm looking for the simplest possible. Like even in the ADC world, what's the simplest possible ADC? I think you could do it. It's like, what's the property of the ADC is resolution, right? I want the simplest possible. What's the resolution of the simplest possible ADC? Yeah, it's a simple 1-bit thing, right? It's a comparator. That tells me only 1 bit of information, right? In voltage, is it higher or lower, right? I put this here in time, it will tell me, is it early or is it late, right? Nothing else. So now I need to figure out, is that enough, right? Or what? So obviously there's some quantization error going on, right? I only know it's early or late. I don't know the precise phase error, but I can model that as saying, okay, I know the right thing, plus there's some quantization error, right? And how does my loop deal with that quantization error, right? It happens at the very input, so it is kind of like a reference clock noise, right? And if we already looked at the reference clock noise analysis, right? The loop kind of tracks it. So if I can characterize what that quantization noise is that I'm injecting into the system, I may be able to manage it, right? So what we're going to do is try to design a loop where we have some phase frequency detector, we're going to talk about it, that gives us directly digital information here. Then we have a digital loop filter, which, by the way, is in the modern technologies a lot smaller and more compact than the previous things that I've shown you. Because remember, in the charge pump, to have small ripple at the output charge pump, I have to have a huge capacitor, potentially, right? And in addition to that, something that we didn't really talk about in the previous noise analysis, remember that R, that resistor, right? That zero resistor has some noise, right? Directly influences the VCO. So there's a noise from the regulating resistor. There's noise from the charge pump as well. Charge pump transistors have noise current. That noise current also integrates and passes through the loop. So you can do all these noise transfer functions. I just gave you a few that are kind of in digital PLLs most dominant because of the digital supply impacting the VCO. But in general, you have all these noise sources passing through with different noise transfer functions to the output. So you have to analyze them all. The nice thing about the digital loop filter, it offers you the flexibility to set more flexibly the bandwidth of the loop, because it doesn't, for the other case, you need to physically change the CP, right? So you have to have it segmented, and there's a whole bunch of problems with all these things. So here you just change some coefficients in the accumulator and you're done, right? Or in the proportional path. So much more flexible implementation to adapt the bandwidth to, let's say, the conditions that are on the ground, right? Because remember, you never know, you're just predicting what the noises are, right? Ultimately, you'll find out what the noise is when you build it and put it in. So you would want to have an adaptive bandwidth PLL, which will kind of retune itself to minimize the noise in situ, right? Ideally. And also, as we put this thing in a DVFS-like system, if I'm changing the output frequency, right? I'm changing the multiplier ratio, essentially. My loop dynamics changes. So I want to be able to adapt basically the bandwidth of the loop so I can get kind of optimum noise performance as I'm tuning in different frequencies. So for that standpoint, also I would like to have a digital filter because it's so much easier to do. Okay, how does that compare to what we had previously? So previously, if you look at what we've analyzed in the PLL basic case, right? We had phi in subtracted from phi out, right? Maybe divided by some factor. Then we had our phase detector charge pump system, right? Which I could characterize So resuming. Okay, good. Let me just hide this. Ah, this. And I don't want this. Okay. So this is what we analyzed previously, right? Now, this is how the simplest visualization or representation of the digital loop looks like, right? I'm gonna try to replace a phase detector with a simple 1-bit ADC or time to digital converter, right? Just tells me early or late. It's a simple comparator, right? And then I'm gonna put some digital filter, right? That has some mix of proportional and kind of integral path that gives me some way to tune the transfer function of the filter to essentially try to smooth out these error signals that are coming in into something that I can use to control the VCO. But in this case, it's not going to be VCO because I don't have voltage anymore. I have just numbers. So it's going to be DCO, digitally controlled oscillator. Right? So I have to have some way of creating a DAC or digital to time converter. Right? That's my DCO now, because I'm changing some digital settings and the delay or the frequency changes on the oscillator. Right? That's going to be the idea here. And then I just have a divider. So if I can do this, then all of these elements are kind of digital, except maybe the DCO. It's a little bit of stuff going on there, but as we've seen, it's inverters. If I can control them with some switches, it's kind of digital, right? Okay. So the name of the game is here that I do it so that I don't destroy, so that this error here that's introduced doesn't destroy all my other sources of error, right? If it's much larger than, let's say, this supply noise error, then I kind of screwed up, right? But if I can bring it down with loop design so that it's actually reasonably small or comparable to the supply noise, then I have a very flexible system. Okay, so, I mean, there's a nice paper by Crossley at CICC, so we're gonna go through some of these kinds of elements that they've done there. But essentially, this additional quantization noise here, because it's kind of a binary thing, like it gives you either up or down, or early or late, if you will, coming from kind of where it intercepts the rising edge of the input clock. It actually creates a limit cycle. It's like a little nonlinear system. It creates a limit cycle in the phase response of the PLL. Right? Kind of, and another way to people call this is bang bang. So it either like sets one target, and then the PLL tries to acquire that, or sets the other phase target, depending on kind of where it's sampling here, because it's a very coarse sample, 1-bit basically decision. Right? So if you're gonna go in detail through the math that we're not gonna do here, you can actually define what that peak-to-peak limit cycle is, because it ends up essentially oscillating the output phase between the 2 points, right? It thinks it's early, it goes there. The loop switches to the other side, right? For a small error immediately to the other side, so the loop has to go all the way back there. And so if you go through the kind of the loop parameters, you can find that the peak-to-peak phase error is essentially a function of the reference clock times the KDCO times these two parameters of the loop filter. And because this is peak-to-peak, I can assume, as with any quantization error, right, that my RMS if this is delta, the RMS will delta square over 12, square root of that. So you're going to get essentially this as the RMS. This is essentially this squared over 12, right? And a square root of all that, right? So you're going to get this to be an estimate of the RMS error. It's kind of estimate because it assumes that the quantization is uniformly distributed within that peak-to-peak error interval. Just like in ADCs, you kind of assume the same thing, that the quantization error is linearly uniformly distributed depending on your MSB or LSB delta, right? Okay, and so if you do that, right, what you do, the way you analyze the loop is that you take this limit cycle RMS as the contribution of this detector. So this noise injected right here. And it's the same as the basically, or it basically gets added to the phi error, right? And then in addition to that noise, you pretend that the rest of the loop is linear. So you find out all the other noise sources like we did in the previous part, and then you add the two together, right? And that's your estimate of the overall noise in the system. And the trick again is that you design this not to be larger, just like in ADCs. You have all your thermal noise and everything, and you have your quantization noise. And you want to set your quantization noise so it's just a little bit invisible or below your other noise sources. Then the ADC is successful, right? Same thing here. You basically tune these parameters, KDCO, TRF, and the loop filter parameters so that this noise is basically kind of on par or slightly less than your thermal supply noise or reference noise in the system, right? And to determine that other stuff, we kind of pretend that the loop has a linear detector, right? And do all the loop dynamic analysis. And to do that, you kind of have to figure out what equivalents between, let's say, PBB and P are. Like PBB is in the digital, P is in the analog. And so they've kind of derived these things. So you can basically analyze this loop dynamics with this analog model as long as you do these appropriate mappings, right? PBB will be dependent on P and KVCO over this gain of the bang-bang times the KDCO, etc. And this gain of the bang-bang will essentially be dependent on, this is kind of your step or the phase error divided by the VCO error. Think of it as this gain BB is kind of a relationship, if you think about the equivalent of the A to D converter. What's my LSB step size compared to the thermal noise that comes in at the input of the ADC? Because thermal noise kind of smears the signal across that LSB, and the relationship of the two will tell you kind of what the gain of that phase comparator is. And so that's what they use here. And once you replace these parameters, you can actually find in the linear analysis that we just did in the previous section, just looking at this type of loop, you can find what your overall output RMS value is as a function of the VCO noise spectral density. Right? And once you add this to the other one, to basically this one over here that we talked about, you can get your overall output RMS or jitter value. And let's say that's something you want to use, plug it in your timing tools and synthesis, place, and route. It will be aware of that jitter coming into your system, right? So here is, they did a little simulation to confirm kind of how does this model work versus omega n, right? So omega n, that's kind of like the bandwidth of your PLL, right? With respect to omega reference. So as you're increasing the bandwidth of your PLL, remember, basically, as we're increasing the bandwidth, we're eating up kind of, the loop is tracking the phase noise of the VCO, right? So that's why the overall jitter is being reduced, right? But then as the loop bandwidth increases, we're now capturing more of this quantization error at the bang-bang detector, right? So that's this excess error here mapped to the output of the loop, right? So you're now setting the loop bandwidth so you can trade off these two noise sources. On one hand, you want a very large bandwidth loop to suppress the VCO noise, but then you start admitting all the extra noise generated by the bang-bang detector, right? Or your digital phase frequency detector. So the sweet spot is somewhere like 1/10 of the reference clock frequency is where you get the smallest amount of noise, right? For example, in this, but it nicely shows that if you do linear theory, right about here, exactly around the 10th or a little bit more, you basically run into stability issues in your linear model or linearized model. But if you actually run a behavioral simulation with fully digital bang-bang, you can actually keep going and see this increase in the excess jitter. Of course, you don't want to work here. You will kind of want to work over here. So that still says that, okay, even linear analysis kind of gets you to the optimal point, and then you just stay there. Okay, so to actually build this, there's a few more bells and whistles you need to add. It's not as simple as this. And the reason is that you want this PLL to be agile. Right? If you go back here, it's not as easy to set up these parameters so that just with the output of this detector, you can react quickly through the proportional path. Because keep in mind that this D is the kind of this timing step that you're introducing from the error, right? The larger the D is, the more gain you're going to get. So the more agile in the proportional path you're going to be, but your error, your quantization error is also going to be bigger, right? So this intersect here will shift this way, right? So your loop will be able to react quickly, but it will have a lot of noise from that reference. So it's kind of like a trade-off you need to make, and you want to try to somehow avoid the trade-off. What's, for example, one idea of avoiding the trade-off? Anyone has any suggestions? Like I get some phase error, it's a step, right? If I choose a small step to make toward that phase error, right? Then my error in that step is small, but it takes me a bunch of time to get there, right? If I choose one big step, okay, I can get there very quickly. But then if the error is somewhere in between, I have a big quantization error, right? So how do I fix that? I want to be more precise about knowing where I need to go, right? Right now, I'm stuck with this one step. I can only make one step at a time, right? So the trade-off is in how fast I get there. If I apply a small step versus I get there very quickly with a big step, but then I have a big error, residual error, right? So what do I need to use to be able to kind of more accurately know where I need to jump? Because proportional path is about immediately solving the problem, right? You just want to see what the error is, immediately try to address it. But how do I know more precisely what my error is? What do I need to use? Can I use still a 1-bit ADC? No, I need more bits, right? So that's one way. So if you look at where digital PLLs are developing, people design a higher resolution time to digital converter. That way it tells them more precisely where they are. So it can generate a larger error signal while maintaining the quantization error at that small delta, right? Because now you have many LSBs, let's say 8-bit or 5-bit TDC has 5-bit TDC has 32 steps. right? But the quantization error is only proportional to the single step over 12, but I can jump anywhere within 0 to 31, right? So I improve. So one way to go is to improve the resolution of the TVC, right? That adds more complication to this block over here. And some people have done that, right? Another way, which is kind of what this paper was doing, is it's kind of like a daring kind of thing to do. You say, look, I'm going to have my traditional phase frequency linear detector. It outputs pulses here. These pulses could be big. So when the error is big, the pulses are going to be big, right? And I can handle big pulses are a good signal. So why not use them directly to tune the DCO, right? Where the problem comes with the linear phase detector is when the error is small. It's trying to output these little pulses. We all know inverters don't react well to tiny little pulses, right? They don't even propagate well, like a few picosecond pulse. You can't propagate it well. Well, that's okay, because this bang-bang loop can take care of that, right? So the bang-bang loop will basically have the integral paths only. So it will take care of these small errors in phase and essentially frequency tracking, right? But the bigger errors in phase are going to be taken on by the proportional path, which goes directly to the DCO, right? So no filtering. And then you have additional kind of regulator loop where you can kind of do coarse frequency tuning and a little bit of frequency lock, et cetera, right? But still, you have these like integral path, which is fully digital bang bang, and then you have this kind of linear path that directly impacts the DCO, but everything is still digital, right? And there are some like little tricks. We're not going to go into that. I think we're kind of close. How do you design the DCO so that these little pulses from the loop can effectively provide you kind of a uniform tuning gain, let's say the uniform KVCO, right? If you do it as pulse control on all the inverters in the ring oscillator the same, you get some fluctuations in this time gain, which you don't want to. So they basically segment it in pieces and do some tricks there to try to smooth out this time gain so that for any DCO phase, it looks kind of constant, right? There's still a little ripple, but you deal with that the other ways. Another kind of interesting point is that now that you have two phase detectors, any DC mismatch between these two can cause a spur in frequency. And so they have additional kind of offset calibration on this comparator to just make sure that its threshold is kind of roughly aligned with what the linear PFD sees. And there's a little calibration there that happens as well. And once you look at the results, it's kind of like what you expect from a PLL. There's this little spur that actually comes from the supply regulator DAC, not the other one, because it's kind of limited, but that's kind of what it is. I want to show you in the last minute just another quick architecture. This is kind of the similar idea, but it uses a little bit different phase frequency detector. It's still kind of like a basically you can call it a bang bang detector, and has a complete digital loop with proportional integral, but that has a few kind of additional things here. So one thing is that the feed forward path, or basically the proportional path, remember, because this one is kind of bang bang, right? It applies a little delta sigma here to try to dither that, let's say plus minus early or late, to try to establish a little bit more precision in where it needs to go, right? So there's a little delta sigma, and of course, delta sigma shapes the quantization noise to be higher frequency, right? And then that goes into DCO, which integrates the phase noise, right? So it basically rejects those higher frequencies. Right? So that's kind of a trick. In a lot of these digital PLLs, you're going to see sigma deltas all over the place because they bank on the fact that there's some low pass filtering happening inside, either the VCO or the loop overall. And basically, this shapes out that quantization noise. Similar trick is here on the fractional and delta sigma in the divider loop, right? So far, we've only looked at dividers that are integer. Remember, DVFS, you want to have continuous frequency scaling, for example, right? So how do you achieve that? You can't scale the ref clock, it's fixed. So you need to have a flexible divide ratio. And so what they do here is they, instead of a normal integer divider, they have basically a multi-modulus divider that they control with fractional and delta sigma. So they're kind of modulating the divide ratio, right? And that causes obviously error, right? But when you analyze how that enters the whole loop, that error is low pass filtered by the loop, right? So that's why you're doing delta sigma dither. So you shape that divider noise into higher frequencies, and then the loop takes care of that, right? So those are kind of the two tricks, and a little bit of, this is kind of like a really cute circuit because it has, you know, for example, the self-timed reset. So this is the Muller C element. So it actually self-times when the two edges are reset. And then this kind of, they call it mutex. It basically is just a winner take all thing that basically figures out which edge comes first. When the edge comes first, they generate an early or late signal based on that, and then the asynchronous kind of resets. But some nice properties about this is essentially it extends the tuning range of the DAC. And then they have some cycle slip, which is important when you're trying to catch up essentially to the frequency lock. And then, you know, people do model these things and then measure. So you can kind of see this limited like cycle peak. It's basically coming from this delta sigma here, right? So these same effects that we talked about, kind of peaking of the quantizer noise, that you can see that this feed forward has a limited resolution, and therefore you still see kind of this the peaking of that noise happening here. Okay, that's all I had on PLLs. Don't worry if you're, this lecture is just meant to give you a feel, right? The basics. We could have like a whole course on PLLs, which unfortunately we haven't had at Berkeley in a long time. But you know, if you're interested in learning more about this, I think there is actually there are videos actually of Elad teaching the course high-speed links 10 years ago with a lot of good PLL stuff. So recommend it. It's a 290C. Bora will talk next time about clock distribution and power supply regulation, and then we're going to tie off the course wrap up after that. Okay, thanks.